Great. Jesse Bettencourt will tell us about neural ODEs.
Hello, yes. My name is Jesse Bettencourt, and today I'll be giving an introduction to Neural Ordinary Differential Equations and how you can use DiffEqFlux.jl to train them. As the name suggests, this is a collaboration between the Flux people and the Differential Equations people, and in particular, Chris, Mike, and Yingbo Ma. Also thanks to my collaborators in Toronto. So some background. Let's begin by reminding ourselves that an ordinary differential equation describes how to move a vector-valued state, z, through time. And this is naturally represented by an instantaneous change of state given by the time derivative function dz dt. And so we'll consider this time derivative function to be the parameterized function f, such as a neural network with learnable parameters theta. And by integrating over this time derivative, or solving the initial value problem, we'll know where the initial state will move. So we don't have access to this exact solution, and instead we have to use a numerical solver. For instance, Euler's method, which is old and simple, as an old and simple method for approximating these solutions by taking step-sized, h-sized steps in the direction of the current gradient, and that current gradient given by the function f. Now, Euler's method is pretty poor. It accumulates error at every step, and this means that even if the step size is small, the solution can quickly diverge. And note that the dots in the animation correspond to function evaluations, and our function, which is a large neural net, will be expensive to compute. So we don't want to do this a lot if possible to avoid. So modern solvers, like the ones found in DifferentialEquations.jl, will have sophisticated evaluation and extrapolation methods, and this will allow us to allow them to adapt their step size to maintain solver tolerance, and we can see that this adaptive solve is much closer to the exact solution and requires fewer function evaluations. Okay, so let's use this background to think about residual networks. Residual networks are like the discrete composition of smaller smaller neural networks called residual units, and here they're f. Here, each residual unit is its own neural network that takes in the hidden state and computes what change it needs to do to that hidden state, and then adds it back. And yeah, so right now, each residual unit is its own neural network, but we can think about instead the residual unit sharing the same architecture and just have the parameters indexed by time. Alternatively, we can have time as an input to the residual unit or as an input to a hypernetwork, which then outputs the parameters for a residual unit. And in this way, we've actually also implicitly defined how the change in state happens in between residual units. But now this looks exactly like an Euler approximation with step size 1. And so we use this to motivate, as before, using a more sophisticated numerical solver, such as an adaptive solver. And in this case, the residual unit is still a neural network, but instead is parameterizing the instantaneous time derivative, as opposed to sort of a discrete change in time, like a ResNet. And so as you can see, we've replaced all of these discrete compositions of residual units with a single ordinary differential equation solve. And so this is the idea underlying neural ODEs. DiffEqFlux makes it very easy to train these models. And so let's see how this works behind the scenes. With a caveat that, given Mike's talk, a lot of this stuff is nonsense and will go away once. Well, I just found that out 5 minutes ago. So caveat, see you at next JuliaCon when we do it with SciGoat. Anyway, like most Flux layers, we just define a simple struct. In this case, our struct has a field called model, which is where we put the Flux model. This is dz dt. The rest of the fields have the other things that are required for the solver to know how to solve the IVP, or the initial value problem, what solver to use, the time span you want to solve for, as well as solver arguments. Then the next step is to just make this struct play nice with Flux, and in particular, we expose the parameters of the struct by saying, oh, its parameters are actually the model parameters. Here's an example of just defining a neural ODE layer. We've supplied some Flux chain as a model. As well, we also want to say things like the solver tolerances and what time steps we want to save for. And so all that happens in the keyword argument field. In particular, we want to be able to control what time steps the solve gives back, because in problems such as classification, we only really care about the end problem, or the end state, whereas if we want to predict time series, then we'll want to use something that returns predictions in intermediate time steps. So if we call a neural ODE layer on an input, this gives us, this dispatches to a convenience function which prepares the initial value problem to be solved. And this is slightly dishonest, but the preparation basically is doing a bunch of tracker nonsense, which again will go away. And what that means is it exposes the parameters that are implicitly defined for a flux model and makes it explicit, which is required for these adjoint solves. And so once it does all of this parameter fiddling, it returns that, or it sends that to another function called DiffEqAdjoint. Now, if we want to optimize, use gradient optimization on large neural ODEs, then basically we have to use the adjoint sensitivities method. And really simply, this method involves solving the forward solve, the normal initial value problem as usual, and then defining a new system whose initial value is the end state of that initial solve, and we solve that backwards in time. And the solution to that new reverse time solution gives you the gradients with respect to the parameters. Now, computing gradients like this by solving an ODE backwards in time does not require us to backpropagate through the operations of the solver directly. This allows us to do things like directly controlling the error in our solve, as well as avoids storing activations, which is very memory efficient. So the adjoint method was already known in the ODE literature, so naturally that means it was already inside of differential equations suite, and in particular was provided through DiffEqFlux.jl. And so all we really needed to do to make neural ODEs work in Julia was just tell DiffEqSensitivities to use the gradients defined on the flux model using automatic differentiation instead of some usual thing where you supply a Jacobian. And then we just hook those gradients from the adjoint solve back into Flux. Okay, so let's just quickly see what this looks like if you're a user. You define a Flux model to be the derivative function. So in this case, we have a chain of conv layers. And the model that we're implementing here is almost exactly the model that was in the original Neural ODEs paper. Right, so we have this Flux chain. Notice that I'm also piping this to the GPU, which again is the old way of sending this model to live on the GPU. And if we also give it a CUDA array as an input, then the entire ODE solve will happen on the GPU as well, which is great. Next, we supply some solver arguments. We'll give it a tolerance, and we'll also say that we don't want to save at every time step. We only really care about the end time because we're doing an MNIST classification problem. So we don't care about what the model was doing in the intermediate steps. Okay, and then we put all of this into the struct as normal, and now we have this neural ODE layer. Also keep in mind that neural ODE layers can't change the dimensionality of the problem. Again, this is analogous to the hidden state of a ResNet. And so to do this, we first have to downsample from MNIST, from the data dimension size, to a desired hidden dimensionality. And we do this with this little down model, which is just some conv layers. And then also, after we're done with the neural ODE solve, we want to take that hidden state and then shrink it down to the dimensionality that corresponds to our number of classes, so then we can classify on the model output. And then so another really nice thing is that our total model will just be a normal flux composition. In this case, a chain. You take the downsampling layer, you have a neural ODE solve inside of it, and then you go from that to the classification. Right. And then these models are optimized as usual. We define a loss, in this case the cross entropy between the model output and the target class. And since earlier we exposed the parameters of this model to Flux, we can just train this entire thing at once by just saying, okay, we're going to train the loss with respect to the params of the model, and that'll go through, get the params of that downsampling layer, as well as the neural ODEs parameters and the FC, and this is what we're training with our optimizer. Just a quick note that when you first run when you first run this, it'll take a little bit of time, even if you've already done a forward solve, because it still needs to set up the adjoint solve. All right. And on the left, you can just see what this looks like. I've just taken a two-dimensional slice of that very high-dimensional hidden state. At time 0, you see what was given by the downsample, the downsampling layer, and then through the animation, you see sort of how the solve separates its inputs. And these are just like the MNIST digits in a batch, and they're colored by the class. So it's cool because you can see that the Neural ODE has learned some dynamics which will separate these classes. Okay, so in summary, DiffEqFlux makes it really easy to put flux models inside of an ODE solve. It also makes it easy to take this learnable ODE and put it inside other flux models. It lets you plug into the differential equation sensitivities and get these adjoint sensitivities, which are an efficient way to use gradient optimization, and then also allows you to use Flux's gradient optimization to train all these parameters in one go. So you'll be able to find this model on the Flux Model Zoo, as well as some other cool things that you can do with DiffEqFlux. Thanks.
So there was something you went by in passing. Maybe you could comment on a little bit more. So when you do adjoint ODE solves and you do the backwards solve, so in a lot of problems this can be very storage intensive.
Yes.
Because you have to store all the intermediate states. But you said something about that doesn't apply to you, and I didn't catch why.
Yeah. So the reason why that doesn't apply to us is because we don't store the states of the initial solve, which is something you could do. Instead, we just define a new new adjoint state, which includes the original dynamics backwards, the reverse of the original dynamics. And then we append this other state here. And then so essentially what we're doing is solving that forward solve backwards in time along with the adjoint solve.
And that's stable?
It's stable for us, yeah. There's reasons to believe that it's not stable in general. Yeah.
There's an option to be able to do checkpointed adjoints because, on neural ODEs, it ends up being stable because of weird properties of the neural network. But for most cases, you want to use checkpointed.
Sorry, so what Chris just said for the live stream is that in neural ODEs, we just are happy to, we don't have to deal with this, but for most cases, you'll want to use a checkpointing adjoint, and that is available as an option. Yeah, so the question was, why don't we just want to do AD through the solver? And in addition to the solver making a bunch of operations that we don't necessarily want to backprop through, it's much more storage intensive. And so when we want to train big models on the GPU, we don't want to also have to store all of the activations corresponding to the operations that the solvers do. In addition, we also, solving it this way allows us to directly control the error of the backwards pass as well. Yeah, because the backwards pass is just another ODE solve, it also has arguments like tolerance.